Hello! Thank you for joining us again for some more geometry. We're going to be tackling perimeter and area in 8.3 and then volume and surface area in 8.4. There are going to be a ton of formulas. Yes, you have to have them memorized for your test because there will not be a cheat sheet. But I am going to go through in these podcasts and try to show you where the formulas come from. And if you know how to derive formulas, it can make it way easier to recall them and use them. Just trying to memorize cold turkey, that's overwhelming. But if you know where they come from and can develop them in your own mind and jot them down, that can make a world of difference for remembering what to use where. Alright, so let's get started. Perimeter and area today. Starting with perimeter. If you just break down the word perimeter, as in a lot of English words, the root word meter means measure, around, measure, and then peri means around. So it literally means measure around something. And that's exactly what you're doing when you find the perimeter. You're finding the measure around the shape. So in the case of a polygon, just add up the lengths of all the sides and that'll give you the measure or distance around the shape. Kind of like if you set an ant at one of the vertices and had it just walk along all the edges until it came back to the same point. How far did it walk? That's the perimeter. So really you don't need any formulas for finding perimeters of polygons because you can always add up the sides. But we'll still show you what the formulas are because sometimes they're handy, especially when you're trying to program a calculator or a computer. Alright, let's start with a rectangle. Well, in this case we have a rectangle, and I'm going to have to count up the units for each side. But, let's say you had your little ant starting right here. Little ant. 1, 2, 3, 4, 5, 6 legs. Let's say he's going to start right here and walk around. Well, if he walks along this edge, he's going to walk 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 units. And then he gets to here and he turns and walks 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 units. And it is a rectangle. It has right angles. Opposite sides are parallel. So opposite sides are also going to be the same length. So this side here is also going to be 15 units. So you don't have to count it again because you know the shape and all that. And then this side here is going to be 10 units again. So to figure out how far this ant is walking, you can add up 15 plus 10 plus 15 plus 10, which gives you 50 units. Now, I don't know if the units are inches, feet, meters, kilometers, whatever. Whatever the units are, that's got to be included in the answer. Because you're talking about distance here, so people need to know whether it's feet or miles or what. So there is a difference. Okay? And that's all you have to do. Seriously. Now, some of you, though, might be looking at this and going, but I learned a formula. I know I had something where I had to plug in. And okay, what did I have to do? Well, this rectangle, you've got length and width. You could let the 15 units be the length. You can let the 10 units be the width. Or if you switch it and make this the width and that the length, it really doesn't matter. But notice that what you're really doing is adding up length plus width plus length plus width. So if you wanted to make a formula, you could say, well, perimeter of a rectangle is length plus width plus length plus width. But mathematicians are inherently lazy. We like to try to write things as short as possible, but still be completely accurate. So we don't want to write out length plus width plus length plus width. So what we do is we say, well, you've got two L's here. L plus L is 2L, or twice L, plus W is 2W, or twice W. And we use that. We say that the perimeter is 2L plus 2W for a rectangle. And you could have used that for your ant. You could have said 2 times 15. Let's erase that. I'm usually a very patient person, but that is really starting to get on my nerves. Alright, 2 times 15 plus 2 times 10. So you got 30 plus 20, which still gives you 50 units. Gives you the same result because it's essentially you're doing the same procedure there. Because multiplication is repeated addition. So you get the same answer. So it's up to you how you want to do that for a perimeter. You can add up all the side lengths for a polygon, or you can try to recall the formula and plug things into your lovely formulas. Totally up to you. I'm not going to be grading you on how you get there, just on whether or not you got there correctly. Alright, next slide just has a picture and the formula in case you want that for reference. L plus W plus L plus W equals 2L plus 2W. Next shape, square. Remember, a square is really a type of rectangle. So you could say, hey, I could just use the fact that a perimeter of a rectangle is 2L plus 2W. But in a square, it's a special case where the length and width are the same. Let's see, in this case, we got 2, 4, 6 units this way, 6 units this way, 6 this way, 6 this way. So you could find the perimeter by saying 6 plus 6 plus 6 plus 6, or 24 units. But then you notice that you're adding up 4 sixes, which is the same thing as multiplying 4 times 6. All 4 sides are the same length, so when you go to find the perimeter, what you're really doing is just multiplying 4 times the side length, whatever that is. I'm trying to make my S's a little fancier so you can tell apart from 5s. Alright, so yeah, multiplying 4 times whatever that side length is will get you the perimeter of the square, or you could still add up all 4 sides. Totally up to you. But this is the same as 2L plus 2W, it's just L and W are the same. 2S plus 2S is 4S. There you go, perimeter of a square, 4 times the side. Ooh, now we got to start having some fun. We have a triangle here. 1, 2, 3, 4, 5, 6 units this way. 1, 2, 3, 4, 5, 6, 7, 8 units this way. And you haven't covered the Pythagorean theorem yet, but this is a right triangle here, so you can use the Pythagorean theorem and get that this is 10 units. But for now, just trust me. Like for now, the problems will have that side labeled with the length. Later, once you learn the Pythagorean theorem for right triangles, you'll have to apply that and find missing sides. Alright, so the perimeter here, just add up the side lengths. 6 plus 8 plus 10. Doesn't get any easier than that. That's exactly what we're doing. We're not, really no fancy formula here. It's just literally adding up those sides. That's all it is. And in fact, when you go to the next slide, perimeter of the triangle, they label the sides A, B, and C. It's A plus B plus C. So again, to find the perimeter of any polygon, that doesn't have to be rectangle, square, or triangle. Just add up the lengths of the sides and you're good to go. Alright. Next, let's tackle area. Perimeter might be the distance around, so it might be like, well, how much fencing do I need for my yard? Area tells you about the space inside the figure. So this might be how much grass seed do I need, or how much dirt do I need to cover an area, a space or something. But what area does is it literally tells us how many 1 by 1 squares would fit inside that shape. No gaps, no overlaps, no leftover space. So you want to perfectly fit see how many 1 by 1 squares would perfectly fit in there. Now, with odd shapes or with shapes that have decimal side lengths, you're going to have to cut up some of those squares to fit them in there. And that can get a little tricky. So you can't necessarily just sit there and count the squares. So you're going to need other methods like formulas to help you. And that's what we're going to look at, like how can we get those formulas. So that's where we're heading here with area. And since you're literally figuring out how many squares would fit inside the shape, the units are going to be square units, like square feet, square yards, square meters, stuff like that. All right, let's start with this rectangle. I purposely gave you a rectangle here where it's a nice perfect number of squares inside that you can count up to get the area. But we're still going to use this to help us figure out a formula for finding area of a rectangle. All right, this rectangle, what do we got? We've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 squares in a row. And we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 rows. So you could add up 15 10 times. Do that. You get 150 squares. Or, remember multiplication is really repeated addition. You can do 15 times 10. You're adding up 15 10 times. So 15 times 10 will get you the same result. So there you go. That's how many squares are inside of that rectangle. And it turns out, though, that even if you didn't have perfect squares inside of there, if you had to like chop up pieces of squares because maybe your length was, maybe the length was 13.2 squares long, and maybe the rows, you only had like 8.9 rows, it would be kind of hard to count the squares in that case. Well, notice that like with even the even number of squares, the length times the width gave us how many squares were inside this rectangle. Well, that's going to be still true even if the squares are like partial squares, decimals. So if we want to find the area of a rectangle, all we really have to do is multiply length and width together, like what we did here. You can do that for any rectangle, as shown in this slide. I'm going to use that for reference. If you want a formula for a rectangle, it's length times width. That'll tell you how many squares are inside that rectangle. Now here's a square, and we're going to count up how many 1 by 1 squares are inside of it. We have 1, 2, 3, 4, 5, 6 across, and we have 1, 2, 3, 4, 5, 6 down. 6 rows of 6. And since a square is a type of rectangle, we could say length times width, which is 6 times 6. But notice you're multiplying the same number by itself, so you could also write it as 6 squared. So you get 36 square units. So with the square, you can do length times width if you want, or just take whatever that side length is. You're multiplying that together, it's the same number, so you end up with just side length squared. And that's how you find the area of a square. There you go, there's the reference. Side times side, or side squared. So square feet, square inches, square miles, whatever it is. Ooh, Now it starts to get interesting. They've given us this lovely parallelogram here. It's not a rhombus because it does not have all four sides the same. It's not a square or rectangle because it does not have four right angles. But opposite sides are parallel, and opposite sides are the same length. And we want to figure out, well, how many squares fit inside of here? Well, in this figure, it's really easy to do inside of this part. I apologize for this not fitting exactly on the grid, but assume that these little corners fit perfectly on the grid. I tried, but couldn't get it to snap into place quite right. Alright, anyways, we've got a rectangle inside of here. So that part we could find the area to easily. Because we got 10 units across there, 8 units there, and we can say 10 times 8 equals 80 square units. But the question lies in, what do we do with these two? What do we do there? Well, you could say, well, I got two triangles, so just find the areas of the triangles. And that's true. You can just find the areas of the triangles, assuming you know how to do that. But we're going to assume you don't know how to do that yet because I have not gone over it yet. I know most of you know how to find the area of a triangle, but this is the way we develop mathematics. Unless we've gotten there yet, we assume we can't do it. So, what is another way to put this together and use the knowledge we've developed so far? And now, create the formula for the area of a parallelogram. Figure out how big this particular parallelogram is. Well, let me go ahead and change my ink color here for a minute. I'll use purple today. Notice that since it is a parallelogram, notice that these two triangles are exactly the same size. They have the same base, same height, same slant. It's just one of them's rotated to be upside down from the other one. But what if we took one of the triangles and moved it and put it like right here? Well, if we did that, we now have a rectangle. Let's see, if we do that, we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 for the length, and 1, 2, 3, 4, 5, 6, 7, 8 for the width. So you can do length times width, or 13 times 8, gives you 104 square units for the entire parallelogram. So we've got the 80 square units from this part, and it turns out that the two triangles together make up 24 square units. Which makes sense because you've got now this rectangle here, 3 by 8, 3 times 8 is 24. So this rectangle is 24 square units plus this 80 square units here gives us the 104 square units. You're going to find out though that for parallelograms, rather than saying length times width, the book likes to say base times height. So I'll switch this to blue. So instead of saying length and width, they go ahead and call this dimension here the base, and they go ahead and call this dimension here the height. So when they go to find the area of a parallelogram, they say base times height. And that height is that straight up and down distance between the top and bottom of your parallelogram. That's your height. So it's still the same as length times width, but they call it base times height because it's slanted, and so it's not exactly like a rectangle having length and width. Instead they say the base, or like the bottom, or the top's the same. So, and then the height is that straight up and down distance, not the slanted distance. If you draw the height segment, it makes a right angle. But there you go, area of a parallelogram, base times height. Now we get to triangle. It's about time. Could have used triangle back there, huh? Made it a lot easier. Well, triangles are tricky because you've got this slant right here. Let's see, this triangle is 6 units this way, 8 units this way. It's just like that other triangle earlier. This particular one's a right triangle, but that's irrelevant for finding the area of a triangle. It's kind of hard to count the squares because we've got partial squares along this slant area here, slant part. But if you go ahead and notice that a duplicate triangle turned upside down and matched up makes a rectangle, you can say, well, I know the area of a rectangle is length times width. Well, the area of a triangle is going to be half of that. Because this triangle here is half of that rectangle. And it turns out you can use this for no matter what the triangle is. The triangle doesn't have to just be a right triangle. And I'll draw a demonstration in a minute. But what they go ahead and do, instead of saying length times width, they go ahead and call this dimension here the base, B, and this dimension here, height, H. So when you go to find the area of a triangle, what they say is do half the base times the height. So like in our case, half times 8 times 6. Which gives you 24 square units. So 24 squares fit perfectly inside this triangle. You know, if you take 24 squares, you've got the whole ones, plus you've got the rest of them cut up to fit the rest of it. But altogether, this makes 24 squares. Now again, not all of your triangles are right triangles, and that's okay. What they do is, like, let's say you have a triangle that looks like this. This dimension here is your base, and this dimension here is your height. And you might be like, well, how does that match up? Well, that triangle is half of a parallelogram. Dang it. Sorry. That triangle is half of a parallelogram. So, area of a parallelogram is base times height. So the area of this triangle is half of base times height. And if you have some kind of crazy leaning triangle like this one, this here is your base. And then go from this top vertex and go straight down to the ground. And that's your height right there. You're finding the area of this triangle, but you're doing half times the base times this straight up and down height from top vertex to the ground. Ground level being like where the base level is. So that's still half times base times height. Because in the case of developing the formula, here's your parallelogram. Okay. So area of a triangle, half times base times height. Ooh, trapezoid. Remember, a trapezoid just has one pair of parallel sides to make it a trapezoid. So a quadrilateral with one pair of parallel sides can be identified as a trapezoid. Some books, it's at least one pair of parallel sides, which means that squares, rectangles, rhombus, etc. is also a trapezoid. Other books, it's only one pair of parallel sides for a quadrilateral. Trapezoid's a little trickier though. I gave you an isosceles trapezoid here, which works out rather well because the triangle on this end and the triangle on this end would come out the same. But remember that trapezoids can be drawn like this, or like this, too. So you really can't do that whole trick of chopping off a triangle, moving it over here, rotating it, and trying to fit it on. And saying, oh, the area is just the base times the height. You really can't do that because, notice this triangle has that one this trapezoid has that one triangle, and this trapezoid has two crazy different triangles. So you really can't do that fancy cutting and fitting together in that way like we did with a parallelogram. But if you think about it for a second, feel free to pause the video right now if you want to think about it and play with it, to think about, well, what could we do to develop the area of the trapezoid based on what we've learned so far? Okay, so if you paused it, you're back. Maybe you figured it out. If you didn't pause it and you're impatient, we're about to go over it. Well, if you did pause it, I'm wondering, did you think to cut it like this? Cut it into two triangles by going from one vertex to diagonally to the opposite vertex. You have two triangles here. Call this base 1, call that base 2. Your height h is the same for both triangles. So you can just call the height h no matter which triangle you're working with. So you can call the height h right here too. So the area of triangle 1 is 1/2 base 1 height. Area of triangle 2 is 1/2 base 2 height. Triangle 2 is upside down. The area of the trapezoid is the area of triangle 1 plus the area of triangle 2. So it's 1/2 base 1 height plus 1/2 base 2 height. So in our case, we've got what base 1 is 18 units. Base 2, again, assume this is like touching the corner here. I couldn't get it to snap on like I needed it to. 14 units. And the height, 7 units. Okay, so we could have 1/2 times 18 times 7 plus 1/2 times 14 times 7. 63 plus 49, which is 112 square units. But you might be looking at that and going, you know what? I see that when I'm adding, the two terms have some stuff in common. Didn't I learn something about factoring when there was stuff in common? Why, yes. Yes, you did. So when you go to find the area of a trapezoid, if you want to make your formula a little bit prettier, you can factor out a 1/2 and an h, and then leave b1 plus b2 in parentheses. You get the same answer. So like in this one, you could have had 1/2 times 7 times 14 plus 18, and you'll get the same answer. half times 7 times 32. See, half of 32 is 16 times 7 is still 112. So you can do it either way. Either you can break it up into the two triangles, find the areas and add them up. That's perfectly fine. Or if you want to remember the formula, it's 1/2 times height times the sum of the bases. And that would give you the answer too. So there's your reference slide for the area of a trapezoid. Alright, so that covers most of the area formulas that you're responsible for polygons. If they give you some kind of wonky polygon you haven't covered, remember too, you can always break them up into pieces. Break them up into rectangles and triangles, shapes you're familiar with. Find the areas of those, and then add up the areas. So there's ways around it, even if you don't have some kind of pretty formula to use. Alright, Pythagorean theorem. As promised earlier, we were going to go over the Pythagorean theorem, because I had that one right triangle where I whipped out the length of that hypotenuse. And I was like, well, we'll talk about it later how to get that. If you have a right triangle and you know the lengths of two sides, you can easily find the length of the third unknown side using the Pythagorean theorem. The sides attached to the right angle are the legs. Label those A and B. The side opposite the right angle is the longest side, or the hypotenuse, labeled C. So in this right triangle here, our legs are the sides attached to the right angle, and then our hypotenuse is the longest side opposite the right angle, and that's our C. So leg squared plus leg squared equals hypotenuse squared. There's all kinds of proofs for this that show that it works. Sorry about that. Ask me that anytime in the show. But I wanted to pull up a video from YouTube where they're using some liquid to show the fact that a squared plus b squared equals c squared. You have this right triangle here. You have one of the legs is length A, and they have a square attached to it that's a by a, or a squared for the area. Then one of the other legs is b, and they have a square attached to that that's b by b, or b squared. And what's going to happen is they're going to rotate this and pour the liquid out of a squared plus b squared into this square. This square is attached to the hypotenuse with length c. C by c is c squared. So they're going to show that the area here, a squared, plus the area here, b squared, is going to fit into the area here, c squared. Pretty cool, huh? There you go. There's like a visual demonstration of your Pythagorean theorem. I don't really want to call it a proof, but you can find lots of proofs out there if you really are interested. Isn't that neat? Okay, I don't want that. Sorry. But lots of proofs if you start searching for proofs. But maybe that little demo I thought would help you to see what was happening there with the formula. Alright, let's do a problem where we have to use two problems where we have to use the Pythagorean theorem to find some missing sides. Alright, let's start with, we have a triangle that's, you want to make sure that you definitely know that it's a right triangle first before you try to apply the Pythagorean theorem. This only works for right triangles. If it's not a right triangle, then you have to use law of cosines or law of sines, depending on what you've got. And in fact, law of cosines will work on the right triangles. So what happens is the cosine part turns out to be 0. So you're left with a squared plus b squared equals c squared. Which is kind of cool for those of you who've taken trig before. So we've got right triangle here. I know that because of the little square corner. We've got a leg that's 10 centimeters, a leg that's 24 centimeters, and we're trying to find C. So we know that a squared plus b squared equals c squared. So we know that 10 squared plus 24 squared equals c squared. Let's see here. 10 squared is 100 plus 24 squared, don't know offhand what it is, 576. Next to my trusty calculator. 576 plus 100 is 676. Alright, I'm not sure offhand. And notice that's just c squared. So to find c, I gotta go ahead and take the square root of 676. Just the positive square roots needed. Technically c squared, if you're trying to solve, you have to take both positive and negative square roots. But we're finding a length, so all we need is positive square root. And the square root of 676 turns out is a nice whole number, and we get 26. And this is in centimeters. So there you go. 10, 24, and 26. Now your problems aren't always going to have you find C. Okay, this next one's kind of similar to the problem, to the triangle we were dealing with earlier a little bit. In this case, they gave us the hypotenuse is 10 inches, one of the legs is 8 inches, and they want us to find the length of leg A. So a squared plus b squared equals c squared. We don't know A yet, so we'll keep it as an A. The other leg, B, is 8 inches. And the hypotenuse, C, is 10 inches. So A squared plus 64 equals 100. Subtract 64 from both sides. You get A squared equals 36. Technically, A is plus or minus the square root of 36. But we only need the positive square root because we're doing the length. Square root of 36 is 6. So A is 6 inches. So there you go. That's how you can apply the Pythagorean theorem. A little bit about the Pythagorean theorem. Named for Pythagoras. You probably guessed that. Greek mathematician. But turns out he probably didn't come up with it. He was the head of a school of scholars known as the Pythagoreans. They were an interesting group. They were it's kind of a secret. They governed themselves and ran themselves like a secret society. They had all kinds of passwords and protocols and whatever. And a lot of the way they ran their secret society, those traditions and things have been carried down through the ages and are in use today in fraternities and sororities, at colleges and universities, and also in groups that the adults are involved in that have their secrecy, such as the Freemasons. But anyhow, and another interesting thing about them too is that at a time where things were predominantly male-dominated, Pythagoreans welcomed females equally. They didn't discriminate based on gender, which is pretty cool, especially in that time period. But anyways, alright, so interestingly, the theorem was probably discovered or whatever by one of his students and then got his name on it. That happens a lot. You're working on your doctorate, you make a discovery, you're doing your research, it doesn't get your name on it, it gets your your professor who's directing your research, their name gets on it. But anyhow, and even then it wasn't first discovered by them. It was already in use before they even existed. Ancient Egyptians, ancient Babylonians, they were all familiar with it and were already using it in their building. Just look at the pyramids. The Egyptians had to have known something about it. With the Babylonians, they didn't know that the Babylonians knew about the Pythagorean theorem until the 1960s. Archaeologists uncovered a tablet in the 1940s And linguists were slowly working on deciphering what it said. And in the 1960s, they finally figured out what it said and realized, oh, this is actually quite a bit of mathematics that was, including the Pythagorean theorem, in use long before the Greeks. But by then, it was too late to rename the theorem, so it'll just keep being called the Pythagorean theorem. Anyways, that's just a little bit of history there for you. Alright, let's go on to circles. Circles are fun. Circle is a set of points that are all equidistant from a center point. A segment from the center to any point on the circle is a radius. A segment from one point on the circle through the center to another point on the circle is a diameter. Notice that the diameter is twice the radius. So this diameter right here has one radius plus one radius, or two radii. Radius in plural is radii, R-A-D-I-I. Alright. Now when the notion of pi was first being developed, pi was defined as the ratio of a circle's circumference to its diameter. You take any circle, if you know its circumference, you know its diameter, or you construct a circle where you know the circumference, know the diameter, the ratio of those two always simplifies down to pi. But knowing that, we can then do a little work and solve for c and come up with a formula for computing circumference. Because we know enough about pi's value. We can either find the circumference and leave it in terms of pi, which is an exact answer, or we can use a decimal approximation of pi and get approximately what the circumference is. As long as we know the diameter. Or if we know the radius, just double it, and that'll give you the diameter. So that's cool. That works out nicely. And then for area, you could try to divide up your circle into little squares, but that gets pretty tricky when on this rounded part. It gets pretty messy. So how do we develop the area of a circle? Well, imagine your circle being divided up into tons of pizza slices, pie slices, whatever you want to call it. I'm getting hungry for lunch, so all of it's making my stomach rumble thinking about it. Imagine yourself dividing this up. It's going to look like a wagon wheel. But let's say you divide it up into so many pieces that this part here is no longer round. It's straight. And let's say you take those pieces apart and you start laying them like this. You do this enough times, you essentially get a parallelogram or a rectangle. If these are infinitely cut to where this is basically straight, this dimension is going to be half of the circumference. That dimension is going to be half the circumference. And that dimension is the radius. So you essentially end up with a rectangle. And you can find the area by doing the length times the width. So if circumference is 2 pi r, half of the circumference is going to be half of 2 pi r, which is pi r, because half of 2 is 1. So the area, length times width, you can do pi r times r. And you get pi r squared. When I was in college, my roommate, her father had to move in with us for a while before I graduated. He asked me one day, we were talking about, I was studying math. He said, hey, what's the area of a circle? How do you find the area of a circle? I said, well, you do pi r squared. He said, what? I said, pi r squared. He's like, no, it's not. I was like, Yeah, it is. It's pi r square. He said, no, pi aren't square. Pi are round. Cornbread square. It's like, oh. I'm a queen of bad jokes, but that was really bad by my standards. But anyways, area of a circle, pi r square. And here you go. Here's your reference slide, circumference and area. Alright, let's do a circle. Let's find these values. Let's say we have a circle, and they tell us, I know, I'm sorry, bad drawing, it does not look like a circle. It's like a lopsided egg. And they tell us the diameter here is 16 yards. Well, if the diameter is 16 yards, and the radius, remember, is half of the diameter. So half of 16 gives us 8 yards for the radius. So the circumference, we can do pi times the diameter. So we can do pi times 16. And actually 16 pi yards is an exact answer. Or we can put this in our calculator. And round. Go ahead and round 2 places. And we could say 16 times pi in the calculator. Let's see what we get. I get 50.26548246. I'm going to go ahead and round it to 2 places. So I get 50.27 yards. And that's an approximate answer. Converting it to pi to a decimal like that gives you an approximation. It's not exact. Leaving it in terms of pi is actually exact. And when you get into higher mathematics, like calculus, you just leave everything in pi, in terms of pi most of the time. Because you'd rather have exact answers. Alright, pi r squared for the area. So we got pi times 8 squared. So we get 64 pi square yards. That's our exact answer. And then we can put it into calculator, 64 times pi. And we get 201.06. Can't quite read my display here. It looks like 19298. My display is going bad. Yeah, so 201.06 square yards for the approximation. Now you might notice in your book, I was just noticing this, instead of writing like square yards, you can also write yards squared. Well, either one of those is perfectly acceptable. Just wanted to let you know about that. Alright, so there's for circle. Now with all this area stuff, you're going to find that in your problems, you're also going to have to do some problems where it says, find the area of the shaded region. Okay, and you're going to have these shapes, like shapes within shapes. They're going to give you some information about dimensions. And then you have to find the area of the region that's shaded. Okay, so this one they tell us 20 inches for one base, 9 inches for another base. They tell us that the radius here is 4 inches. Okay, so area of a trapezoid here, half height times the sum of the bases, half, well, the bases are 20 plus 9. The height, they don't directly say what the height is over here on the trapezoid, but they tell us the radius of this circle. So then we know, okay, going this way is also 4, going here is also 4. So the diameter of the circle is 8, which also is going to be the height of the trapezoid. Half of 8 is 4 times 29. 816 square inches for area of the trapezoid. And then for area of the circle, pi r squared. So pi times 4 squared, 16 pi. So that's around it's 50.26548246. On these problems, I don't like to round until I'm done, because otherwise it can mess me up. Alright, so there's the circle. And then to find the shaded region, basically the shaded region is the trapezoid minus the circle in it. So just do area of the trapezoid minus the area of the circle. So do 116 minus the basically 50.27. And you get about 65.73 square inches. And that's the area of the shaded region. Again, don't round until you're done, like at the end. Or like in this case, I knew that rounding wasn't going to change the answer when I was subtracting. But hey, subtract and then round usually. And you'll find too, pay attention, like in my math lab it'll probably say use your pi key, but it could also tell you just approximate using 3.14. And on tests it's possible too, so pay attention to whatever the directions say to do. Whether they say to use the pi key in your calculator or say to round and use 3.14, because that will affect your answers. And my math lab gets really picky about the decimals in these problems. Alright, and you've got lots of those. So the shaded regions, often you can find them results by doing some subtracting. Sometimes it's also finding the areas and adding, so just think critically about your shaded regions. Alright, last concept in this lesson. Going back to conversions again, like we were doing back in chapter 7, but now we're dealing with square units. This slide shows you the square unit conversion factors that you're going to need to be familiar with. If you think about a square that's 1 foot by 1 foot, you know the area is going to be 1 times 1 or 1 square foot. But also keep in mind that this 1 foot is 12 inches. So you could also find the area by doing 12 times 12, which gives you 144 square inches. So 144 square inches equals 1 square foot. Same idea with the square feet and the square yards. It could be 1 yard by 1 yard. So the area is going to be 1 square yard. But remember that a yard is the same as 3 feet. So the area could also be 3 times 3, or 9 square feet. So 9 square feet is the same amount of space as 1 square yard. Or let's say you have it in terms of centimeters and meters. The square could be 1 meter by 1 meter. So in that case, the area is 1 times 1, or 1 square meter. But remember, 1 meter is the same thing as 100 centimeters. So the area can also be 100 times 100, or 1 with 4 zeros, 10,000 square centimeters. So that's how they get those conversion factors. You can find any conversion factor you need for square units by thinking about that. Thinking about, what is it they eat? What is 1 foot equals 12 inches? Square those, and there's your conversion factor. All right, so let's look at a problem where you have to do that. I have to use those. Let's say you need to convert 396 square feet into square yards. Well, we know there's 9 square feet in 1 square yard. So proportionally, that's the same as 396 square feet to how many square yards? We don't know yet. We're going to find out. So 9 times x equals 1 times 396. So x equals 9 times 4 is 36. 9 times 4 is 36. So x equals 44. So you get 44 square yards. Or let's say you're trying to convert 9 square meters to square centimeters. Well, we know that 1 square meter has 10,000 square centimeters. So 9 square meters is how many square centimeters? So 1 times x equals 9 times 10,000. So x is 90,000. So we're talking about 90,000 square centimeters. 90,000 little centimeter by centimeter squares will fit in a square that's 3 by 3, or 9 square meters. So there's your conversions there. So practice that definitely. Make sure you know how to do those conversions too. All right. Well, that wraps up all your square units, perimeter, and area. Next lesson, you're going to go from 2D to 3D. Volume and surface area. Volume is going to be cubic units. Surface area is going to be back to square units, but it's all going to be about 3-dimensional shapes. So tune in for that. That's where it gets really fun. But definitely practice in 8.3. Commit those formulas to your memory. I suggest knowing how to get them rather than just trying to memorize them cold turkey. Good luck with that, and I'll see you again soon.